Hello everybody, welcome back to data analysis. So this is the second part of the lecture that we began last time where we talked about confidence and prediction intervals. And the title of that lecture, we also included alternative measures of model fit. So today we're going to talk about alternative measures of model fit, and I will turn us around and get us started. Before I actually talk about alternative measures of model fit though, I want to include a quick side note about something we talked about last time. So just a quick refresher. Last time we talked about, of course, prediction and confidence intervals for the betas, confidence intervals for the mean of the prediction, and then prediction intervals for the actual y values themselves. And when we had this dinosaur picture, I mentioned that these looked like something like 80% prediction intervals or something like that, just eyeballing it. I actually found the paper that this comes from, just again looking at this Physiology of Dinosaurs Wikipedia page. I was able to trace back and find the academic paper that these results came from, and it turns out that these intervals are actually 95% confidence intervals. So a confidence intervals, and again this is for this expected value of y given x, and they're not prediction intervals, as it turns out. So, yeah, so just eyeballing it, apparently I got it wrong, but still, the point of this graphic that you're presenting regression information along with quantifications of your uncertainty, tracing back through Wikipedia, and finally finding this academic paper, and then seeing what they had in the footnote that they said that this is an illustration with 95% confidence interval. Surprised that the confidence interval for this dinosaur regression line is so wide, but I guess that's what happens when you only have 10 data points. All right, so let's jump back into where we're going to pick up for this lecture, and that is with alternative measures of model fit. So the big quantity that we've used for model fit so far is mean squared error and root mean squared error, right? And so we're going to be talking about alternatives to root mean squared error. Root mean squared error being a decent measure of model fit, but we're going to talk about some other ones. So the first one is mean absolute deviation. Okay, so remember in RMSE we take the average squared distance between the values and the predictions, right? So this is root mean squared error, or so this is mean squared error, root mean squared error, we have the root, right? So instead of quantifying the difference between the truth and the prediction with a squared distance, in mean absolute deviation we quantify it by taking the absolute value between the truth and the prediction. Okay, so this is the definition. This is mean absolute deviation, and we abbreviate it MAD. Okay. Sometimes people call it mean absolute error. Okay, so either way, you have this mean absolute deviation, mean absolute error, both synonyms for replacing the squared distance here in mean squared error with absolute values. Okay. The other alternative measure of model fit that we'll talk about is R squared. So R squared is defined as the following. So what you do is it's 1 minus, okay, and then this is the sum of y, the truth, minus the prediction squared. So this is a certain squared error over, this is y minus y's mean. Okay. So this has an attractive property, okay. It has some unattractive properties that we'll talk about, and historically I believe that R squared has been overemphasized in the regression world, but we'll talk about that in a little bit. But the nice quantity about R squared is that it is unitless. Okay, so think about it this way, right? If y has a certain units, right, y hat also has those same units, y minus y hat, so this is whatever the summation is, has those units squared, but then we're dividing by whatever those units are in the denominator here. So whatever the units are in the numerator cancel with the units in the denominator, and R squared ends up being unitless. Okay, What's nice about that is that, so it's a measure of model fit that actually doesn't have the units of y. So if you were to come to me and said, hey, I have an r squared, I could come to a completely different linear regression model with completely different y's and say, oh, I have a different r squared, and those numbers are actually comparable. So we can use both of these in conjunction with RMSE, that is MAD and r squared, and caret, this package that we've been doing that wraps together a bunch of different interfaces in R. So we do principal component regression, we do ridge regression in caret. Caret automatically prints mean absolute deviation r squared as well. So it's just worth learning them and understanding what they tell us. So I will just make one other comment here. So if you run summary on a linear regression model in R, R will print you multiple r squared, okay, and what it calls at least multiple r squared and adjusted r squared, okay. So a multiple r squared is just this value, okay. This is just translating. So this is multiple r squared, just usually called r squared. But adjusted r squared adjusts each of the squared error terms in here by their bias. Okay, so what adjusted r squared would do is take this numerator and divide by 1 over n minus p minus 1, right? And what is this? This is our estimate of sigma. This is our estimate of s squared, right? Let me grab a eraser. This is our estimate of s squared. And so when you do adjusted r squared, you're basically saying, hey, I'm dividing by some squared errors. I'm going to adjust for, in this r squared that I'm building, I'm going to use unbiased estimates of sigma instead of the biased versions. Okay. And then again, dividing by 1 over n minus 1 here. The reason is that this y hat comes from estimating p plus 1 parameters. This y bar, all we're estimating is a mean, which is 1 parameter, so that's 1 here. Okay. So adjusted r squared has this piece here, whereas multiple r squared, which we'll just call r squared, doesn't. Okay. So if you run summary, you'll get r squared for free. All right. So first, let's talk about mean absolute deviations. So the pro of mean absolute deviation is that it's more robust to large errors or just large measurements in general. And the reason for that, and when I say more, I mean as compared to RMSE. Okay. The reason is that x squared, right? That's how we quantify errors in mean squared error and then root mean squared error as well. It grows more quickly than x squared, right? So something like x squared, or this is like x, looks like just a sharp point, and x squared, has sort of this curving, and it's sort of in the tails, right? It U's up, whereas this absolute value of x has these lines that go out, right? So so when you have large values in this squared, right? They're very large, right? Large x values are very large in their y values, whereas large values here are less large, just because of the rate of change there. A con is that, and I should just say, so I say this is a pro, right? This is a pro because the mean absolute deviation is sort of more robust to outliers, right? If you had one large outlier, it tends to not skew your results as much as it would RMSE. So a con here is that the mean absolute deviation is not differentiable, right? Because of this kink of the absolute value function, this kink at 0, the mean absolute deviation is not differentiable. And so, let's say you wanted to, similar to the way we've constructed our least squares estimator, let's say you wanted to have an estimator which minimizes mean absolute deviation, right? So optimizing over it is difficult because we don't have differentiability here at the origin of the absolute value function, okay? So it's difficult, it's not impossible. The estimator which minimizes mean absolute deviation, it's called the LAD estimator for the least absolute deviation estimator. Okay, so even though it's difficult, we can define one. It's called the least absolute deviation estimator. So this is a flashback to your optimization class. So optimization alert. So if you are taking in this class and have not taken a linear programming class, this is probably not going to understand this bit, but for those of you who have taken linear programming, it's going to be a little of a blast from the past. So the mean absolute deviation estimator, the goal is to minimize as a function of b, that's our estimator, this mean absolute deviation quantity, right, where I've plugged in xib for my prediction, right? So this is our goal, right? We can rewrite this objective function as a linear program, okay? Here's how we'll do it. And so if you haven't seen this trick, it's actually pretty cool. And this trick applies when you are minimizing some function of absolute values. Okay, so we have a linear function of b in here, right? And then we have absolute values. And so what we're going to do is I'm going to introduce this new dummy variable t. Okay, so I'm going to introduce this new dummy variable t, and I'm going to introduce 1t for each of the observations. Okay, so I'm going to have 1t for each observation, and I'm going to minimize this quantity. Okay, and so instead of minimizing these sum of absolute values, I'm minimizing the sum of these t's, subject to two constraints. Okay, the first constraint is that ti, each of the t's, is bigger than yi minus x beta, and the second one is that ti is bigger than negative yi minus x beta, or x beta minus the predicted value. Okay. So what's happening here is, you know that, of course, depending on the sign of yi minus x beta, right, yi minus the absolute value of yi minus xib, it is equal to yi minus xib or negative yi minus xib, right? So depending on the sign, right, if this thing is positive, if yi minus xib is positive, then the absolute value is just this, and if it's negative, then you take the negative of it to get up something positive, right? So there's only two outcomes for this quantity. So when we set up this extended problem where we've introduced this auxiliary variable t and these extra constraints, what we're saying is t is bigger than the positive part of the absolute value and the negative part of the absolute value, right? So because it's bigger than both of these cases, it's bigger than the absolute value, right? So this is greater than or equal to, ti is greater than or equal to the absolute value yi minus xib, right? And not only that, but because we're minimizing this expression in t, right, we're going to choose the t value, which is the minimum. So we're going to push right on up against whichever constraint is tight here, right? And it's going to be whichever of these values is larger, and whichever of these values is larger is going to be the positive one, i.e. the absolute value. Okay, so so just with that reasoning, right, this t is going to push up against the constraint here, which is tight, right? And that tight constraint is going to be the absolute value. Okay, so then ti is going to be equal to the absolute value at an optimal solution, and then we're minimizing the sum of these ti's, which just is going to end up being minimizing the sum of the absolute values of these yi minus xib's. Okay, and so this is a linear program. Okay, so we have a linear objective function in t, and then linear constraints in t and b, right? Because remember, x is fixed, y is fixed. These are data inputs. Okay, and so since this is a linear program, the least absolute deviation estimator can be computed with as a linear program. Okay, so for those folks who have seen linear programming, that's how we can compute it. We won't talk about details of that, but computation is not too difficult, right? I say it's difficult. It doesn't have a closed form solution the way that the least squares estimator does, where we can write x transpose x inverse x transpose y, but we can solve for it as a linear program. Okay, so that's the least absolute deviation estimator and mean absolute deviation. So let's talk about r squared for a little bit. So as I discussed previously, r squared is unitless. Okay, that's nice because we can compare r squared across regression problems. Another thing about r squared is that it is between 0 and 1. We can sort of talk through why that should be. Let me erase this this notes that I had from before talking about adjusted r squared. But why should that be? Why is this between 0 and 1? Okay, well, first of all, it's definitely less than or equal to 1, right? Because we're 1 minus something that's positive, okay? But why is it greater than or equal to 0, right? Well, the reason is actually here. So y hat I, right? This quantity, this enumerator, is smaller than the denominator. Okay? Why is that? Well, this is true because y hat, right? We talked about this before, but y hat, we're just predicting y with a constant, right? And then when we have y bar here, we're predicting y with a constant. But in this numerator, we're predicting y using p predictors plus 1 intercept, right? So there's 1 intercept, and then p predictors 1 intercept. So we're definitely going to do better. If you give me extra information, I can do at least as good as I can in the denominator where I only have a single predictor, right? Because I can just set all of my predictors equal to 0 and just have the intercept term equal y bar, and that's just a special case. So this, since this quantity is going to end up being larger than this, or since this quantity at the numerator is going to be smaller than the denominator, this quantity is going to end up being less than or equal to 1. This whole quantity is less than or equal to 1. So we're subtracting 1. So 1 minus something that's less than or equal to 1. That quantity is going to be greater than or equal to 0. All right. This is some benefits of r squared. So a con about r squared, and this is something I think this is quite problematic, but I think that people think, well, you know, r squared, unitless, 0 and 1, you should definitely use it, right? But still, in using r squared, how do we know what's actually good, right? Let's say, so it's unitless, and you can look back at the expression and convince yourself of this fact, but larger in r squared is better. So basically, if r squared is closer to 1, that's good. If r squared is closer to 0, that's bad. So it's not a loss function the way that root mean squared error and mean absolute deviation. You know, smaller is better. With r squared, larger is better. But still, how large is good, right? If I come to you and I say, okay, you know, here I have an r squared which is 0.75, you know, are you going to say, great, you know, that's a great model, you've done very well, or, you know, will you say, well, I expected better than that? Or if I have an r squared that's 0.5, right? What's a good model? It's hard to know without context, right? So you can't just come and present me an r squared and say, great, you know, I have a great model, because we still don't know. Is it possible to get 0.85 from a r squared with another regression model? Potentially, and then you'd prefer that one. The other con about r squared is that it actually doesn't address model fit very well. So I'm going to talk about this in a slide here in a little bit. But the idea of r squared has the following problem, and that is that for a fixed variance in our model, so remember this is coming from our constant variance assumption, r squared can actually be made arbitrarily small even if we fixed our variance just by increasing the variance of x. Okay, so that is counterintuitive because, right, if we say, in some sense, right, the sigma squared is like an idea of how much noise is in the problem, right? If sigma squared is large, then this is telling us that the noise is there's a lot of noise and we expect it would be hard to estimate, right? But what r squared has this unattractive property that for fixed noise in epsilon, right, or for fixed noise. For fixed variance in epsilon, r squared depends on the variance of x, okay? So truth about linear regression, our course text has some interesting discussion on this point, but this is counterintuitive, right? The fact that your measure of model fit actually depends on the variance of x and not just sigma, not just the noise in the problem, okay? Because of this drawback, the fact that, you know, even though it's unitless, that it doesn't necessarily address model fit as well, it's being used less. You'll tend to find that folks who learned regression some time ago, you know, tends to be the talk tends to be dominated by r squared. I think more recently, folks are focused on things like RMSE. And again, you know, why would something that's sort of suboptimal live on? Well, it's taught by those who were taught it, right? So I suggest using RMSE and mean absolute deviation. They don't have this unattractive property that the measure of model fit depends on the variance of x. But there are some times when you cannot use RMSE and means absolute deviation because you're comparing across two models with different y measurements. You know, if you had a y that you were predicting and you had a transformed y, and you wanted to compare them, well, RMSE and mean absolute deviation would have different units, so you couldn't compare them, and then you would basically have to use r squared. Okay, so let's talk R a little bit. Let me just jump forward really quick and make sure. Okay. So this is the code. This is just extending the code that I used for prediction intervals and confidence intervals. And so I'm going to pick up computing the lat estimator, the least absolute deviation estimator. The package that I'm going to use for this is called L1pack. Okay, so L1pack has this LAD function where you can compute a least absolute deviation estimator. Okay, so I'm going to load it up. And I'm going to create a LAD estimator predicting, and again, actually I have to load up this again. But this is continuing this example from the previous, from part one of this lecture, which was predicting percent body fat using, for example, hip circumference. Okay. So here I'm going to build a least absolute deviation estimator predicting percent body fat from hip circumference. Okay. Here's just a plot of a scatter plot just to get some context. So hip, percent body fat, unsurprisingly, hip circumference goes up, percent body fat goes up. But that relationship is sort of surprisingly linear, right? So here is here's the least absolute deviation estimator. Oops. I'm relying on some things that I haven't run yet. I'm relying on this linear model, and I'm relying on this new data frame to predict. This new data frame, just a quick reminder, I plugged in a bunch of x points distributed across the range of hip. That's what I'm predicting on. So here's the least absolute deviation line. Okay, and here's the least squares estimator line. Okay, so you say, well, doesn't seem like much of a difference. Totally agree. But let's say, for example, just as a thought experiment, let's say that we added an outlier. Okay, so this happens. You know, let's say that, I don't know, some lab assistant that we had who was recording all this information about folks. Let's say that they had an error where, you know, instead of where there's an outlier. Okay, so what I'm going to do here is I'm going to add a new data point to my data frame, which has somebody with hip 120. Oh, excuse me. No, here's what's going on here. I permuted these numbers. Okay, so let's say the lab assistant meant to enter percent body fat and hip, accidentally entered hip percent body fat in the wrong order, right? So this is just a data entry error. So if you had 120 and 55, you know, that would be sort of like up here in your scatter plot. You know, well, okay, that's sort of large, but that's not completely unreasonable just based on what we see by these points, right? But if you were to switch and you had percent body fat was 120, right, which is a percentage over 120 or over 100, that doesn't even make sense, right? If you switch them and then your hip circumference was 55, I don't know, what is this, inches? This would be especially problematic, right? I guess this isn't inches, this is centimeters, because 55-inch waist is a very, very large waist. All right, anyways, point is, this data point is nonsensical, and I'm just sort of throwing it in to say, if you had a situation where you had outliers in your data, what happens to the least absolute deviation line, okay? So I'm going to rerun my model, okay? So I'm going to, here's my plot, okay? This is my scatter plot. Here's my outlier for my data entry error, So this is problematic. Now I'm going to build a least absolute deviation estimator, and I'll build a least squares estimator again, okay? And I'm going to add these both to the plot. So this is the least absolute deviation estimator, and here's the least squares estimator, right? So do you see how much the least squares estimator responded to this data point, right? These lines were basically the same, and then afterwards, after throwing this outlier, the least absolute deviation estimator roughly goes through the center of the points still, right? But the least squares estimator is not going through the center of the points anymore, all because of this one outlier, right? So this is just an example sort of showing what I mentioned in the slide, which is that mean absolute deviation estimator is more robust. Just as a quick note, I mentioned that that the least absolute deviation estimator can be found using linear regression. L1 pack actually can be found, excuse me, I said using linear regression. The least absolute deviation estimator can be found using linear programming, right? L1 pack actually does not do that. It uses another method, but if you felt so inclined, you could definitely code that up as a linear program. Okay, so I want to illustrate this example or I want to give an example demonstrating this drawback of R squared that I mentioned in the slides. And in particular, that is that it depends on the variance of x. Okay. So here I'm going to create a quick example. So I'm going to set the seed, create some x sample. So x here is uniform from 0 to 5. I have 100 samples. Create some epsilon, some noise terms. That is sample 100. 100 samples, mean 0, standard deviation 1. And build a y1 and a y2, right? So in this example, right, so if I plot y1 as a function of x, okay, these x's, let me just do this again. Plot y2 as a function of x. I'm going to make this color equals red. Oops. Just going to plot these on the same scale. Okay, so here's y and x. Okay, so I maybe have a couple of points off the plot here, but we see the general trend. So what's happening here is that if we were to put the ideal line through this y and through the black points and through the red points, the noise around them is the same, right? The reason we know that the noise around them is the same is because we actually built the noise around them as the same, right? This is the same epsilon sample being added to both lines. So there's this ideal line. The first one has slope 5. The second one has slope 1, right? And we're adding this noise to it. And so we should think that, generally, because the noise in both of these models is the same, that we should have similar R squareds to them, right? But unfortunately, we don't. So if we fit a regression line from y1 onto x, right, we get an R squared here, which is 0.983 for the first one. And we get an R squared for the second one, which is 0.692, right? So even though, putting a regression line from the perspective of the noise in this model, in these x's and y's, putting a regression line through the middle of these points is the same difficulty, right? The r squared is much higher for the black points than for the red points, right? So that is a bit counterintuitive. The reason actually that this is true is that y in general has more variance. Okay, so y1 has more variance than y2, and that means the spread of all the y's is larger for the black than for the red. That is what's skewing. You can look at the formula and convince yourself that that should be the case, that this will happen, this adjustment. But from our perspective and from the perspective of measuring model fit, this is a little bit counterintuitive, right? So just wanted to mention that as an example. All right. So let's wrap up alternative measures of model fit. So what I want to say about them is that, similar to p-values, you can use mean absolute deviation and r squared to supplement RMSE, right? Just again, similar to p-values, the idea is it's sort of another perspective on what makes a good model. You can look at decreasing test RMSE. You can look at what does the t-test say about what coefficients are important? What does the f-test say, or the log likelihood ratio test say about what coefficients are important? These are another perspective on measuring, if you have a good model. RMSE is one measure. You can use mean absolute deviation and r squared similarly, right? Just use them to get another perspective on if you have a good model, okay? At this point, right, because I say we have so many ways to measure model fit, how should you choose, okay? This is just my workflow. This isn't how you have to do it, but for me, I start with RMSE, okay? And then if I have two models which are roughly comparable with respect to RMSE, then I'll reach for other measures of model fit. So I'll say, well, their test RMSE is similar for these two models. Are the p-values or the coefficients similar, given that I satisfy the modeling assumptions necessary to apply these hypothesis tests? Then I could look at mean absolute deviation and say, well, if RMSE is similar but mean absolute deviation is a little smaller for one, then I can rely on the one with smaller mean absolute deviation, right? Here's what I've written out almost exactly what I was just describing. If I have two models similar in RMSE but one has lower MAD, right, that tells me that, it suggests at least that outliers or large errors are influencing my model, right? Because RMSE is getting large for one of the models, but the mean absolute deviation is lower, right? So if there were no outliers, you would generally expect these, if RMSE is similar, you'd expect mean absolute deviation to be similar. Just again, given similar RMSEs, I could lean on MAD as a secondary criteria. Okay, so that's all I have to say about alternative measures of model fit. So I will see y'all next time.